good evening, sir.
Uh, Please confirm that you can hear me and you can see my screen.
Yes, sir.
Okay.
Yeah, you are audible as well as screen is visible.
Screen is not visible.
Visible, sir.
Visible. Okay. Sorry. Mhm. Please mute yourself. Just a second. Okay, we'll start now. Good evening. My name is Shaktu Shide. I'm a PhD scholar at IIT Bombay, Department of Electrical Engineering. I am working on electrical machine design for my PhD, and I take this class, doubt clearing classes of power electronics, which is taken by Professor Elumanand from ISB Bangalore. This session is a weekly session. Every Monday, 6 to 8 p.m. I take this session. So this is the eighth uh, doubt clearing session, which will be covering the contents of ninth week, actually, because we are trying to synchronize ourselves with the assignment problems. So magnetic circuit design. So two kinds of DC-DC converters we have studied till now. Okay, one is, broadly speaking, isolated. Isolated we studied later. First, what we studied is non-isolated. Okay, now in non-isolated DC-DC converters, what we need is the inductor, and in isolated DC-DC converter, what we always need is a transformer, and sometime we need inductor. So when we say magnetic circuit design for a power electronic converter, we mean these two components, design of these two components, inductors and transformers. Now last week, since a question came, we had a discussion on how to design inductor for flyback converter. I discussed, but um, the process is pretty much the same for any kind of inductors or transformers, on how to uh, choose the core, how to choose the winding, how to make sure that the winding will go into the core and all. So a large part of this class was already covered in the last class. So the thing is, this apart from what we discussed last week, one more systematic way of uh, magnetic circuit design was discussed in the lecture, which is that area product. Area product was discussed. Area product is nothing but AC times AW. AC is the area of copper area that we need, and AW is the window area that we need. And once we get the multiplication of AC times AW, which is AP, this AP gives us the area product, and which actually helps us in choosing the core from the data sheet. So if you open the data sheet of course, you will get to see that the course are, just a second, you will get to see that the course are you getting any noise from my side? Just a minute. No, it's fine. Okay, that the course are enlisted with their part numbers, different types of course and their AC. Also AWAP are given. This AP is the one which we look for in the core catalog and find out which core we need. Last class I said that we will discuss synchronous buck converter in this class, but the person who asked for it is as of now not yet present in the meeting, so I would ask you to go ahead with your questions, your doubts. We will first discuss them, then maybe sometime we will discuss synchronous buck converter. Yeah, doubts from you.
Solution to assignment, can you please discuss, sir?
Okay, so questions we will discuss. Have you watched the lecture videos of this week?
Yeah, so for this, I have not gone through this lecture video.
Okay, I'm not very sure how much the solutions will be comprehensible without going through the lecture videos, but we will go through it anyway. But like any other day, we will start with doubt discussions.
Okay, no issue.
Yeah. No doubt. It's quite good. Then we will go through solutions. Yeah.
Sir, there is a doubt in the forward converter transformer flux. Uh, Sir, actually, when in the forward converter on the primary there is a switch.
Yes.
So if you turn on the switch, current in the primary will be increasing. And sir, once you turn off the switch, uh, the voltage across the inductor will reverse, which will forward bias the secondary
Yes.
diode in the secondary, which is the reason for the energy transfer from primary to secondary. Sir, in this, once we turn off the switch, the flux in the core actually reduces to zero. Which means at that time in the secondary we will have very high voltage.
No, in the secondary do not have very high voltage. See, the thing is that if you consider an ideal transformer, then an ideal transformer has infinite magnetizing inductance. In other words, it draws zero magnetizing current from the source, which means the core flux is zero, right? So whenever a current I2 flows in the secondary and a current I1 flows in the primary, I1N1 I1N1 is equal to I2N2, and as a result the net flux is zero in the core, right? Now when you are not considering ideal transformer, then you have to consider a finite magnetizing inductance of the transformer. Now this is the case when we need a reset winding. for the forward converter. Now if we do not have the reset winding, then yes, you are right, the secondary voltage is suddenly very large. Not only that, the whole voltage actually comes in segments, the whole circuit experiences large voltage. Ultimately it gets dissipated across the switch. But to avoid that only, we have a reset winding. Now if there is a reset winding, then what is happening is the voltage that is coming here, the voltage that is coming here, if I write this as V1 and if I write this one as V3, then V1 is minus N1 by N3 V in. So the voltage that is coming here is this much, the primary. So the inductor, the magnetizing inductor current, if I call it IM, that is dropping across this voltage. So minus N1 by N3 V in equals Lm dim dt. So it's a linear drop like this and becomes 0. So the slope is finite. And if you see, now if I write V2 also, we have V1 equals this. So what is V2? V2 is N2 by N1 times V1, right?
Yes.
Sorry, yes.
Yes.
No, did I write something wrong here?
No, it is V1. V2 equal to N1 into by N1
Times N1 by N2, like this. So we have this. Now you see V2 value. So what is now V2? V2 is basically minus N2 by N3 V in. Now look at the voltage polarity of V2.
Okay. Yeah, it is also.
So it will not be able to drive any current.
Okay. Sir,
So the negative voltage does not come. I mean it comes, but what you are saying, a large negative voltage, that does not come if there is a reset winding.
Sir, okay. Sir, can you please comment on this flux waveform in the code?
Flux waveform in the code.
Yes, sir.
One thing I drew here wrong, that's why it's coming like this. This diode, if I call it say D1, if I call it D2, this diode D1 actually stops the current from flowing for this voltage. Now if you want to see the, just a second, yeah, if you want to see the flux waveform in the code, ideally no flux, and practically it depends on in what way you have designed the reset winding. So if you see here, in this expression, if you see N1 by N3, this ratio, could you please mute yourself? N1 by N3, this ratio gives the resetting voltage of the magnetizing current. Okay, so larger this voltage means larger this value of N1 by N3, we can say that our N1 and N2, and these were decided from the requirement of voltage stepping up or stepping down. So we can say smaller the value of N3, sharper is the fall of the magnetizing current. Now if you design it exactly at the boundary, we this is the boundary that we derived last class. M3 by naught is 1 by t minus 1. So if you exactly design it at the boundary, sorry, 1 by 1 minus 1. So if you exactly design at the boundary, then how will the flux look? The flux will look like this. It will keep touching 0 like this. But if you have a value of n3 higher than what is given by this equation, then your flux will die down faster. Then you will have a discontinuous flux waveform in the core. But this discontinuity is no way related to the discontinuous conduction mode of the circuit. Continuous conduction mode of the circuit depends on the inductor current, the secondary side inductor current. Okay.
Yes, sir, it is understood, sir. Sir, if you okay, this is for forward converter. This is okay, sir. If you this is understood.
Hmm.
If we go for the flyback converter,
Hmm.
uh, in the lecture it is drawn like the flux is continuous, but if we look into the operation of the converter, it seems that flux in the primary is dropping to zero before flux in the secondary is increasing. Flux
See,
because of secondary current is increasing.
the thing is, in flyback converter, first of all, we cannot call it a transformer. Although in many cases it is mentioned as a transformer, but I doubt whether it can be referred to as a transformer. Why? I will tell you. See, in flyback converter, you can still explain the operation if you consider it to be an ideal transformer in forward converter. But in flyback, you cannot even consider it as an ideal transformer. So the way this thing works is not a transformer, it works as a coupled inductor. Okay. Now,
Okay.
now you see the flux that you are saying, that is a common thing to both the sides, the primary and secondary. So it is the
Yes.
primary, it is the secondary. Then now if I draw the current, if the primary current looks like this, then the secondary current will look like this,
Yes.
and the flux will look like this.
Yeah. So that
Then
is where my doubt is.
what is the question?
So the question is actually we are at the intersection point. The flux is increasing and again it is decreasing. Sir, in this at the peak of the flux value,
Hmm.
the flux actually drop the flux because of the primary current actually drops to zero. Uh,
No, see the thing
before,
is, okay, in the secondary side we do not have any active switch. Okay. Now if you look closely, let us draw the transformer properly. Okay, this is a better way of understanding. Hmm. Give me some time, I will draw the transformer.
okay.
So I'm drawing it with proper sense of windings. Now if I draw it this way, then I can say this is dot and this is dot. Okay. Now you see, if I say that this switch is closed, means the current is flowing like this, current flowing like this. So a current is flowing in this fashion. So the flux in the core is this. Okay. Now when this current I1 is increasing, means when the switch is on during this time, this flux is increasing, right? In this way it is increasing. Now
Yes, sir.
if we look at this secondary winding, so the secondary winding is experiencing a flux like this 5. So if the flux is increasing, the secondary winding will try to create a flux upwards, right, to oppose the flux. Now if it tries to create a flux upwards, you see it will try to push a current like this, right? So that will not be possible because of the diode, so the secondary side will be off when the primary side is on. Understood? Now what is happening is we are opening the switch. We have opened the switch. Now once we open the switch, then this flux suddenly tries to drop. Okay, this flux suddenly
Yes, sir.
tries to drop because there is no source of flux. We know that mmf is flux times reluctance. If mmf suddenly turns 0, flux will try to become 0. Now as soon as it just tries to be 0, that means look at the flux at the secondary limb. This flux in this direction is trying to drop, so the secondary side will now try to create a flux which is downward. Now again apply the right hand screw rule, you will see that now the secondary will try to create a current like this. So this will immediately turn on the diode. So as soon as the switch in the primary side is opened, that would immediately turn on the diode in the secondary side. So there is no way that the flux will come to 0 in any moment.
Yes, sir. Actually, if you go with the other explanation, like if we open the switch, voltage across the primary winding will reverse, and according to the dot polarity, the
Hmm.
bottom terminal on the secondary will become negative and the top terminal will become positive, which will forward bias the diode, and
Hmm.
it will drive the load. So
Hmm.
if we go with that explanation, then actually for the voltage to reverse on the primary side, the current should uh, go to minus di by dt. The
No,
current
see
on the
the
switch current
voltage,
through the
if
switch.
you when you open the switch, if you look exactly at that moment,
Mm,
if you see, then what is happening, the flux that is trying to drop, it is creating a voltage like this, and hence a voltage like hence a voltage like this in the primary.
mm,
But even before this voltage could do any harm or any damage to anything, the diode turns
mm,
on
mhm.
and lets the flux drop linearly,
So diode turns on the flux because of the primary, because the secondary current builds up.
goes down.
So,
The stored energy is now going to the load. Is it clear?
so it is happening before the diode turn on is happening much faster than the switch turn on.
No, no, no. You forget the speed of switching. Forget the speed of switching.
Okay.
You just assume that all the switchings are instantaneous. They take zero time in turning on and off. Okay. Then also, when you turn off this switch S1, okay, when you turn off,
Okay.
means opening,
Okay.
at that moment, for a very short time, the flux phi tries to reduce. Very small time.
Okay.
And that decrease is enough to turn on the other diode.
Yeah. it is not completely. It is on the initial phase of coming down.
What comes down?
The flux is not coming down drastically, but it is in the initial phase of.
Yes, for a
Uh,
very short time. Now, if you consider not ideal, so if you consider practical switching where the flux really takes time, where the switches really take time to turn on, then that delay will cause some voltage spike in the switches one, and also on the leakage inductance that will cause, as a result, the switch voltage you will see something like this, which should have ideally been a square wave like this. This spike will rise on it.
okay, sir. Sir,
Yeah.
in our flux reset approach in the forward converter,
In the
can you
what?
get, sir?
Yes, go ahead.
Sir, in our flux reset approach in forward converter,
Mm,
we considered the leakage inductance to be zero.
yes.
Uh, Sir, if we consider the leakage inductance,
Mm.
uh, what is the flux reset?
If you consider the leakage inductance, flux reset does not change. See, I have introduced the leakage now. Only thing that
Okay.
happens is that the when you are turning on the primary switch, energy not only gets stored in the magnetizing inductance, it also gets stored in the leakage inductance. But
Okay.
when you are resetting the flux, means when you turn off the switch and the flux is getting reset, then only the energy stored in the magnetizing inductance can be reset, whereas you cannot do anything about the energy stored in the leakage inductance. So what happens is, it either gets dissipated across the switch, or if you have a snubber, then it gets dissipated in the snubber resistance.
Sir, this leakage inductance, I
Mm.
have a doubt with this. This
Yeah.
leakage inductance is directly proportional to the is directly proportional to the permeability of the air around the core, because that is where the leakage flux flows.
Yes, but leakage is a non-ideality, so there are many things that uh, affects. But leakage is always, see, if you have a core, uh, say a double E core like this, suppose, then around whatever you have here around the windings, see, if you have the windings here other than the core, are all at the permeance of air, be it the former or other things, all is there. So leakage means definitely yes, that is going through the air, but it is much more complicated. We cannot directly say. I mean, there are other things also related to it.
No, sir, my question is whether the leakage flux is there proportional to the permeability of the copper wire or the permeability of the air.
That's what I'm saying. The permeability of copper and permeability of air, there is not much difference.
Oh.
Copper is also what is that called? Diamagnetic, no? But it is not magnetic. So it is as good as air in terms of relative permeability. I think the mu of copper will be very close to 1. It will be, right?
The magnetizing inductance is that proportional to the permeability of the core.
Yes, magnetizing inductance basically, suppose you have a transformer, say you have two windings of a transformer, you remove one winding. Okay, now what you are left with? You are left with uh, one inductor, one simple inductor you are left with. So whatever the inductance value, that is the magnetizing inductance. I was expecting more questions today because this magnetic circuit design is quite important as well as interesting topic.
Sir,
Yeah.
I have one more question with the dot convention.
Mm-hmm.
Sir, I have one more question with the dot convention.
Hmm.
Sir, usually you place the dots on the core with respect to the sense of the winding on
Hmm.
the core.
Hmm.
Sir, but there is a other convention also that the voltage of the dotted terminal with respect to undotted terminal on both the sides will be same. Will be
Hmm.
of not same, will be of same
Same
polarity.
polarity. Hmm.
Yeah, and also the current entering the dotted terminal will produce a negative flux in the core.
See, the thing is that there are
I want
several
to.
ways of expressing the same thing. At the end, they all burn down to the same thing. Um, you can take any one. You can what to say? You can follow any one of them, but that would hardly matter. It's not that the conventions are different. That's those are different ways of saying the same thing.
All the
When
three, sir.
uh-huh.
Uh, Different ways of saying the same thing. Whether the with respect to sense, if you say that is same as saying the dot convention with respect to the input and output voltage and current. There are three ways of saying this. I think that is what I understood, sir. With respect to sense, we can place the dot. With respect to the output voltage polarity,
See,
with
the
respect to input and output voltage.
thing is at the end the dot and all everything that comes from the winding only. Okay. uh, how we are winding the transformer, depending on that the dot comes. But now suppose I give you a transformer in your hand and you cannot see the how the windings are. Even if you can see the windings, it's not very easy to make out the sense of winding if they are very dense enough. So you are left with a transformer like that. What will you do? You are asked to give dots on the terminal. Okay, then what will you do? You will simply do a polarity test. You will simply polarity. What you will do? You will short circuit these two terminals.
Okay.
You will if this is a high frequency transformer, you will give a high frequency, say some 10 kilohertz, 20 kilohertz, whatever, sinusoidal here. And what you will do is you will use an oscilloscope. Okay, an oscilloscope whose channel 1 you will use, sorry, whose channel 1 you will use to see the voltage of this terminal. Channel 2 you will use to see the voltage of this terminal. Okay, now what you do is, the first step is that you put dot somewhere in one winding. Say I put dot here in the winding, right? Now whenever I am seeing the voltage, I am seeing voltage with respect to this, means point A with respect to point B, and there point C with respect to point D, right? Now I have put dot at point A, at point A. Now I see that voltage AB is this.
Okay.
Voltage AB is this. On the oscilloscope, at the same time, I will also look at the voltage CD. The way I have drawn the transformer, voltage CD will come like this. It will come like
Okay.
this. So you can understand that it's opposite. So you shorted B and D, C is on negative polarity, so dot will be here.
Okay.
It's like this. So it is basically the same, in the different way of saying the same thing. The one of the definitions goes like this, that I discussed, that if the current is going through the dot terminal and if the current is increasing, then wherever there is a higher potential will have the dot terminal. What does it mean? That means that if you now draw equivalent circuit of the transformer without considering the coupling, that means say if I have dot on the lower side and if this is I1, then it will be this polarity, mdi1 dt, and if this is
Affected.
I2, this fashion. And to make things simple in DC-DC converters, I told you that since V equals L di dt, so di dt positive means V positive, so increasing current means positive voltage. So if I have dot positive in one winding, it will be dot positive in all other windings, like that. You can simply remember like that in DC-DC converter. If you have multiple windings, if you ever get confused, simply follow this way of drawing the transformer, putting the dots as per your drawing, then draw the whole complete circuit, then analyze the flux and analyze the circuit. Okay, anything else? Any more doubt from this week or last week? No doubt. Okay.
Sir,
Yes.
sir, you said in flyback converter,
Hmm.
we actually use the coupled inductor instead of a dual transformer.
Hmm.
Sir, in that, how, which means that two windings will, you mean it will store some energy higher compared to the transformer in forward converter.
Yes. In fact, we want it to store energy. In transformer, we do not want the core to store energy.
Yeah, because in forward converter, we need transformer because in the same cycle it is transferring energy. Is that
Yes.
the reason, sir?
And whatever energy got stored accidentally due to non-ideality of the transformer, we had to give it back using the reset circuitry, either dissipate it or give it back to the source, because you do not need it. Okay, then anyway.
But in both circuits, sir, but
Mhm.
in both forward and flyback, in both primary and secondary winding, the old second balance need to be maintained. Is it, sir?
Yes, yes,
Both the terms,
hmm,
both forward and flyback.
yes. For the forward converter, you cannot say both primary and secondary because only this magnetizing inductance is the one, the inductor. This is these are not inductors. Okay, these are not inductors. This is a circuit representation of transformer. So these are not inductors. This is an inductor. This magnetizing inductance is an inductor. So if you apply volt second balance here, uh, it will work. I mean, you will get to see that integration over v dt equals 0. In fact, this volt second balance of this magnetizing inductance only gives us the required number of turns of the tertiary winding to make sure that it can discharge completely before the next cycle starts.
So here, old second in this magnetizing inductance itself is sufficient.
I'm not saying sufficient, means that is the only, means here only you can do and here you can do. If you do volt second balance in this inductor, you will get the voltage relation between input voltage and output voltage, whereas volt second balance in this inductor will give you the condition for complete discharging of the stored energy of the transformer.
But in flyback, in the winding itself we can do because it is
Yes,
inductor.
yes, you can do volt second balance in both the places. Okay, then we will start solving the problems. In the meantime, if you remember something, you can ask me. And I was asked to discuss synchronous buck by someone, but he is not present.
Hello.
Yeah, hello.
Sir, I have a doubt in converters.
Hmm.
So, in case of isolated converters, we are using transformers, right?
Hmm.
So, uh, but usually transformer they won't work for DC because of constant flux. But in this case, we are using switches. So, because of that switching, the change in flux will happen. The energy will be transferred from primary to secondary. Is my understanding correct?
Okay, so a common myth, I would say, a myth that goes is that transformers don't work in DC. There is a completely wrong statement which we are taught. I was also taught at some point by some book. Okay, but the thing is that it's not the transformers don't work in DC. They do work in DC. I will show you how this myth came. Suppose I have a transformer here and I give a DC voltage, right? Now if I look at the equivalent circuit of it, then this is the equivalent circuit, right? This is the magnetic inductance Lm. Now I have a voltage V DC. Now there is some current I flowing here. Now what is this I? If there is no load in the secondary, then just a minute. Then what do we have is VDC equals Lm di dt, right? Now how will the current look? The current will look like this. The current will look like this. This is I. Okay. Now, so I can say this is Im. This is Im. And now if you connect a resistance R here, now whatever VDC times number of turns, that will appear here, and for a input voltage of VDC we will perfectly get an output voltage of VDC with a transformer. So transformers do work in DC supply, but the problem is with this magnetizing current Im. This magnetizing current will keep rising like this, and the values of Lm or inductance that we generally have seen millihenry of, maybe even if for large inductance my hundreds of millihenry and all, even with that large inductances also, even a small VDC will suddenly give rise to a very large current. This linearly increasing magnetizing current will suddenly become very large, so that either the windings will burn if the supply has capability of that much of current, or the supply will trip, right? That is why at transformer don't work in DC at steady state. Okay, so transformers do work in DC, but in transient zone. At steady state they do not work in DC. But the thing is, in case of say if I take the example of forward converter, whenever we are applying DC voltage in the primary, the current is increasing. The current is increasing like this, just like any other transformer. But the thing is, at this point we are also turning off the current, turning off the switch, so the current is falling, and we are providing a reset circuit so that the current can fall. The current can fall, it falls like this, and this whole thing is calculated. We know from our design how much our Lm is going to be, everything. If I write V equals Lm delta I by d Ts, to us everything is known. That's why we know how this delta I will be, and we know what will be the RMS current, and we know how to design the inductor and everything. That is why we can keep everything under control. This is the way it works. But again, if you see, it is not working in DC, because if you look at the inductor, if you look at the voltage across the magnetizing inductance, it looks like this. When you are turning it on, it is VDC, the input voltage. When you are turning it off, it is minus of N1 by N3 VDC. So for DTS amount of time the voltage is this much, the rest amount of time the voltage is this much. So it's an AC at okay, it can be like this also. At steady state it's an AC, but if you talk about transient, transformers can work in DC. So when you are making the statement transformer don't work in DC, you always say at steady state. At transient they do, and if you have enough capability to supply that power and supply that much current, and if the windings can take that much current, it will keep working in DC, ideally speaking. So one statement I made in the last class, I think, that what we study in our electric machine course, capital V1 by V2 equals capital I1 by I2, I2 by I1 equals N1 by N2. This thing we study in our machine course, but in power electronics I will say I do not think that it is not true in machine. in machine we are not that interested in instantaneous values, but a more general statement is small v1 by small v2, that is instantaneous values, equals n1 by n2. So if you give DC to a transformer primary, you will get DC in the transformer secondary. But at the end, if you look at the steady state operation, yes, they're working in AC only. Steady state operation, they cannot work in DC. Is it clear? Vinay asked the question, right?
And also,
Yes.
yes, sir, it is clear. And sir, for in case of inverters, is there any effect from switching? If we increase the switching frequency, so what is the effect on the output and the input voltage, sir? Means,
Increase in switching
is there any
frequency.
effect from switching? Yes, sir.
Ideally speaking, no. Only effect, ideally speaking, okay? Ideally speaking, the switching frequency Fs, that has no relation with the gain of the converter. V output by V input, it no way affects the gain of the converter unless the mode of the converter is changing from DCM and between DCM and CCM. So if there is no change in mode between CCM and DCM, then variation of switching frequency does not affect the output voltage for a given input voltage. What it affects is the size of magnetics, that is a higher switching frequency means smaller inductor, smaller transformer, that is because smaller required magnetizing inductance, that is ideally. But practically speaking, apart from these things, what happens is the switching loss. So power loss due to switching, that is a direct that is proportional to the switching frequency Fs. So increasing switching frequency increases the power loss linearly. So if you want to go for very high switching frequency, even our regular topologies are not suitable, or maybe regular ways of switching are not suitable. What we opt for is called something as resonant switching. We discussed it some time back, very briefly though, what is resonant switching and how it is used to reduce the switching losses.
Sir,
Yeah.
in a DCM, the transfer ratio is not going to be the same
No.
because of there the quantity of FS is also going to matter. FS and load, everything is going to matter. No?
Yes, that's why I said that unless there is a
CCM
switch
it will
between
not
CCM and
matter.
DCM, CCM it will not matter.
But in DCM it will matter.
It will matter, yes. That's why I'm saying that if it does not switch between CCM DCM, I mean goes to DCM, then in CCM the relation does not matter. For DCM, yes, the relation changes. The relation doesn't change. The ratio or gain, whatever you get numerically, that changes.
Sir, are we going to discuss the magnetics of flyback?
Magnetics of flyback I discussed last week. How to design and all in detail we discussed.
Sir,
I have to see that lecture.
This part you see we discussed it in detail. From this
Designing
part,
of transformer.
yes, this part we discussed. Slot fill factor and everything. Window area, how to calculate window area, how to select the required wire from the SWG table. We discussed everything.
That AP approach is there, no, sir?
Yes, so what I
area
did,
product.
yes, area product, that I think I gave some hint about it. I myself did not recall it till last time that uh, we already calculated the required AC, right, from the required RMS current and the permissible J. We can calculate the required AC and we can calculate the required AW. So AC and AW are related by slot fill factor, and the AC times AW is AP. That will help you to select a core from the catalog.
So AP is different from CCM and DCM.
See, at the first thing when we are designing a converter is that we have to take care of all these things. If you see that the load is a variable load and it is never an infinite variation, always the variation is given to the designer, that the load will maximum vary between these 2 points. The designer knows it, and if the designer then wants that, okay, whatever might happen, I will not let the converter go out of CCM, he can design the magnetics and the frequency of the converter in such a fashion that if the load is inside that given range, the converter will never go outside the CCM. Now he will design the required AC for the maximum load and the required AW and everything. The design of magnetics is a later stage. First comes the design of the converter. There itself a decision must be taken where I want to keep the converter. And
So,
if at all you want to switch between CCM DCM, we have to design the transformer keeping the worst condition in mind.
sir,
Yeah.
sir, while we are discussing about the transformer now, so the transformer working DC in transition state and not in steady state.
Hmm.
Uh, Answer in that statement I have a little bit doubt because we have all the isolated converters working in steady state only with the DC.
Hmm. No. See, if you this is why I showed you this waveform. Look at this waveform here.
Yeah.
If you look at the voltage of any magnetizing inductance of a transformer in any converter, at the end you will get bipolar voltage in all of them.
Okay. So even though we give DC across a magnetizing inductance, we are getting AC.
Yes.
So it will work fine in steady state also, sir.
Yes.
Okay, but what is the meaning of the other statement you made that at
What is
steady
the
state
meaning
it
of?
will, the other statement you made that the transformer will not work in DC at steady state.
So if you give a pure DC across any winding of a transformer, it will not work for long. After a certain time, something will fail. Either the transformer will fail or the source will fail. You have to make sure periodically it is getting negative voltage also, such that the average voltage is zero.
So you are saying that across a magnetizing inductance, pure DC is given.
Yes, if you do that, then something will fail after some time, after a very short time, either the supply or the transformer. And also the circuit will never come into steady state. It will always be in transient. Just look at this circuit. Or maybe look at this circuit. These two circuits will they ever be in steady state?
No, sir. In the inductor, current will be increasing.
In this case, the current will keep increasing. In this case, the voltage will keep increasing linearly.
Sir, lot of noise is coming.
Yeah, I know. Actually, I am in a different setup today. This will be a problem for today only. Next week onwards. All right, we will briefly discuss. Last week we ended our session saying that we will discuss a little bit about what is that called? Synchronous buck converters.
Yes, yes, sir.
The thing is that we have already buck converter, but in spite of that, why at all we need a synchronous buck converter? So we'll start with some small statistics, which are all of these are taken by Professor Mukul Chandorkar's class note slides. Is that this is one very widely used application of synchronous buck converter, which is the power supply of the CPU cores. I don't know whether you have idea about this, but when I was taking this class for the first time, I was really surprised to know this thing, that you see these are known to us. Uh, this this is only i5, 8th and 9th. Okay, now I think i9 is there in the market. The machine that I am using right now has Ryzen 9th generation, I believe, some octa core, whatever. So this 65-watt power rating was there, but now the processors have even higher power rating. But on the other hand, the voltage range is only 0.25 to 1.52 volt. So basically, what you have, or the power supply for the converters, for the processors, the cores, is this much of current at only this much of voltage. A very fine voltage ripple tolerance is acceptable. That is one thing. We will not discuss about it, or maybe discuss about it. But the most important thing is that a very high current, 42 ampere or maybe 60 ampere, in for higher processors. There are processors like I've forgotten, some Skylake or something. Skylake, I believe, they require even more current, but the voltage rating is more or less the same. So the question that comes is how to supply such a large current with small voltage. Now, what is the problem? The thing is that, see, this is a regular buck converter. Okay, we have diodes here and we have switches here. This is the inductor and this is the capacitor, and then comes the load. The thing is, when we open the switch, the current free wheels through the diode. And the voltage drop across the diode is quite large. Or in other words, the RDS on of a diode is quite large. If it is large, then what is happening is that my required power supply, my required output voltage is very small, maybe say 1.5 volt, whereas a current of 42 ampere is flowing through the diode. I don't say 42 ampere is flowing through the diode. So this cannot be done with a diode. We have to have a solution with a much smaller on-time resistance. So that is realized by this. So if I draw a MOSFET, okay, I am drawing IGBT kind of things, it is easier to draw, but these are MOSFETs. No, let me draw MOSFETs only, it will create wrong impression. So this is a MOSFET, this is another MOSFET, like this, and they have body diode. They have body diodes like this. Now what is happening is, a MOSFET, when you turn on a MOSFET, it can carry current in both directions. If the channel is, when the channel is formed, this MOSFET, when the channel is formed, it can carry current in both directions. Can carry in this direction, also in the other direction. So when if you look at the this MOSFET, when the switch S1 is turned off, the current that was flowing, that will go through this MOSFET upward, like this, in this way. So that is the objective of using synchronous buck converter, to supply very large amount of current with a small drop in voltage. Now a small thing that I said we will discuss is that the DCM operation of synchronous buck converter. For a regular buck converter, what happens? Say at some load, if you have this kind of current, then maybe at the CCM DCM boundary, you have this kind of current, okay? But if you reduce the load even more, the current becomes discontinuous. Why so? Because this is a regular buck converter. The current is like this. So when this switch is opened, this current drops to 0. That was flowing in this way, drops to 0, and then stays at 0 because there is a diode here. It will not let any current flow on the other way. But for a synchronous buck converter, we have switches in both the cases, and both the switches can allow you currents in both direction. So what happens in a synchronous buck converter, at DCM, the current looks like this. At DCM, the current looks like this. This is the inductor current. As a result, if you look at the inductor voltage, it is just like a buck converter or synchronous buck converter at CCM. So the relation V output by V input equals D, that does not change in a synchronous buck converter even if it goes to DCM. All right. One more thing about synchronous buck converter is that, say I am drawing the buck converter 1 second, okay? Say this is the buck converter, right? I can always replace the diode with a switch because this diode is nothing but a switch. So if I look from this point of view, it is a buck. Now see, if you look from this point of view, it is a boost, isn't it? The boost converter looks like this. This is a boost converter. See, so from this point of view, it is a buck converter. From this point of view, it is a boost converter. If I call this voltage as V1, if I call this voltage as V2, and if I say that the duty ratio of this switch is D, then the duty ratio of this switch must be 1 minus D. So V2 by V1, if I write from the buck point of view, is D. On the other hand, if I write it from the other way around, from the boost point of view, I have V1 by V2 is, just a minute, let me write it here. V1 by V2 is 1 by 1 minus D, right? Because when we write equation for a boost converter, we write the duty ratio D. If I write V output by V input equals 1 by 1 minus D, this D is the duty ratio of this switch, which is 1 minus D in this case. So it comes out to be 1 by D. So you see these two matches. V2 by V1 is D. So basically a synchronous buck converter can work as a bidirectional converter. Bidirectional converter, so it can allow flow of power in both directions. It is very much used in, you know, two quadrant operation of DC motors, where you can connect the DC motor in this way. So when you are breaking the motor, the power can go back to the supply, and when you are in the motoring mode, it will make the power flow from left to right in motoring mode. In generating mode, it will make the power flow on the other way around. Another use of synchronous buck, it can allow power in both directions. So that's all. There is some more advantage of this with respect to switching. The switching loss is much less in this converter because of the diodes. The diodes, when the primary switch S1 is turned off, this current goes through the diode first, so the voltage drops to 0.7 volt. Then, because anyway the switch takes time to turn on, so when the switch is turning on, it sees a very low voltage. So this switch more or less goes through a ZVS. Turn on. So the switching loss is less. Anything else, or else we have to now jump into the questions? Okay. The first question is, the magnetic circuit shown in the figure consists of rings of magnetic material in a stack height of 2 centimeters. So it actually looks like this, and this is 2 centimeter, this thickness, this depth. The ring has an inner diameter Ri 3 centimeter and outer diameter R of 4 centimeter. Assume that the iron is of infinite permeability, okay, and neglect fringing effect in the air gap. So you try to understand the, okay, let's know what do you need to find. For n equals 75 air gap length this, calculate the inductance. So you try to understand the significance of this sentence. The iron is of infinite permeability. What does it mean? It means that whatever reluctance this winding sees comes from this air gap only, okay, and neglect the fringing effect in the air gap means whatever thickness we have been given, what is it, 4 centimeter 3 centimeters, so whatever 1 centimeter thickness we have been given here, that is the path of the magnetic flux, right? Now we have been asked to find out the inductance. So
that is the path of magnetic flux in the air gap.
Yes, means the flux is flowing like this. In the air gap, generally what happens is the flux looks like this. Especially if you are very close to saturation. Okay. But we have been
So
asked
that
to,
area, the effective area of cross section increases.
yes. So we have been asked to find out the permeance of this path only. The permeance of this path only. Oh, inductance L. L is, we know that it's nothing but n squared. Permeance, we have discussed this many a times, and permeance is what? Mu A by L, right? And this is air, so mu is mu naught. Area is 1 centimeter times, what is the air gap length? 0.5 centimeter, 10 to the power minus 6 divided by, what did I do? No, sorry. Area is this area, this cross section area of the air gap. So mu naught, that is this thickness, 1 centimeter, into the depth of the core. You understood, no?
Yes, sir.
This is the core. So the area is area of this. So the depth of the core, which is 2 centimeter, and this, which is 1 centimeter. That is the area, divided by the length of the flux path, which is 0.5 centi. Oh, everything is centimeter. Quite large. Everything is centimeter. So can you please find out the permeability? Mu naught is 4 pi 10 to the power minus 7. Please confirm you are getting something like this. Are you getting something like this?
Yes.
Okay. So this is permeance. So what is inductance? Inductance is just 75 squared times this. So answer times 75 squared will give you this in millihenry. So multiply with 1000, some 0.283 millihenry. Okay. All right. So now we look at this fringing. Can you tell me that if we still consider infinite permeability of the magnetic material, but now if we consider fringing, the new L value that we will get, say L primed, will it be lesser than L or greater than L or equal to L?
Greater.
Sir, if it is not air gap,
It is air gap.
So the inductance will be larger, right? Because this A will be larger.
Why is L larger?
This area of cross section will be larger.
Yes.
So per
Or in other words, the flux now has other parallel paths also. So it is now getting more paths to flow in parallel. That means reduced reluctance or increased permeance, so increased inductance. So it will be more. So if you consider fringing also, it will be more. The thing is, when the flux flows, say if you have a core end like this and another core end like this, flux is flowing in this fashion. When the flux flows, it does not understand whether it's iron or whatever. It does not understand. What it understands is what is the mu r of it. What is the mu r here? What is the mu r here? What is the mu r here, here? That all it understands, right? And it is just like a current. It will try to flow through the smallest resistance. Smallest resistance means highest highest permeance. Now you see R equals mu L by mu not mu R A. Okay, so basically what you see, if I now draw some lines here, see if, with blue, say this is one line, this is one line, this is one line, this is another line. All these lines are possible paths that the flux can take. Okay, possible parallel paths that the flux can take, out of which the flux takes the least reluctance paths, or maybe the least reluctance paths see the most flux flowing through it, and the highest reluctance paths see the least flux flowing through it, just like in electrical circuit. Now suppose you are operating at or near saturation, or maybe above saturation, maybe say near saturation or beyond saturation, maybe at say point X or point Y, maybe you are operating, suppose point Y you are operating. At that moment, the mu R of the material, of the iron material or whatever magnetic material you have taken, that has reduced a lot. So if I now give number to the path, say this number if I give 1, this number if I give 2, before saturation the permeance of 1 was much larger than the permeance of 2, but at or beyond saturation the permeance of 1 has now become very close to permeance 2. So the flux will now see throughout this area, the flux will now see a medium whose permeance is more or less the same, so it will more and more take these paths, because to the flux it doesn't matter where from it is flowing, it only understands mu r. More and more it will flow like this, or in other words, closer or beyond saturation you work, more fringing we will get to see. This is kind of interesting point to note. If you can use softwares like say ANSYS is a paid software, or maybe if you can use softwares like FEMM, it is a free software. You can verify these things there. If you reduce the mu r of the material, more and more flux will bulge out. Okay, we'll now go to the next question. FEMM software full form, that is some finite element method magnetics. You can just search for FEMM, you will get the software. Yes, go ahead.
Sir, yeah, after saturation, as you said, the flux will be bulging out.
Even more.
Sir, then, yeah, even more. Then in the not only in the air gap, then the entire core, the flux won't be confined within the core, right?
Yes, 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 that is true. So if you look, now the thing is that if you say if you are very close to saturation, very close or maybe beyond saturation, then this core, you can say it has become invisible in the air. From a magnetic point of view, you can see that this core has become almost invisible in the air. It is now, its properties, its magnetic properties are now very close to that of the air. So the flux will, which you have pointed out correctly, throughout the area it will tend to bulge like this. These parts also will get to see a lot of leakage. Okay, any doubt in this question? We will see this question, next question. Then an inductor is made by winding 10 turns on a ferrite core which has an air gap of 0.1 millimeter. The inductor is supplied with 100 volt DC across its winding for 50 microsecond in 100 microsecond switching period. During this time, the current through the inductor reaches to a peak value of 5 ampere from 0 ampere. Calculate the permeance of the core. Okay.
Sir,
Yep.
एक डाउट है कि ये when we are going to calculate the inductance with a gapped core, that time we are not going to take μr at all, because some gap core gives the for particular gap some μr,
You should actually.
because it is the value is going to vary as gap is going to increase or decrease like that.
So what are you talking about? What consideration are you talking about? Mu r of the
L
material.
is in material total equation. L is equal to mu 0 mu r AC into n square by Lg. Okay, the mu r is going to change as per the air gap.
Yes.
It is not going to be
No,
one.
mu r cannot change. How can mu r? Mu r is a material property. No.
But when it is gap core, they are telling that for gap core you have to consider mu r whatever the manufacturer is going to give. Mu 0 is okay. For air, we have to take mu r 1 and mu 0 4 pi into 10 raised to minus 7. But for gap core, mu r value is going to change.
No, it cannot.
For gap core.
I think what they mean to say here is that, say, if you have a, say, this is relevant to this problem also. So if you have winding like this, then the flux that is flowing, that sees two resistances, two reluctances. So if I draw
One reluctance.
just a minute, if I draw an electrical equivalent circuit of it, then it is like this. So this is Rg, reluctance of the air gap. This is Rc, reluctance of the core.
Core.
This is mmf, which is pushing the flux. Right now, Rg, that will depend on the air gap length by mu naught times air gap area, whereas Rc will depend on length of the core, mu naught mu r, area of core. Right. So I think
Yes.
when they are saying that when you say for gap core mu r changes. No, I think something else, or maybe they wanted to make some equivalent statement. Looks like
equivalent statement. Equivalent statement. When
that mu r can never change.
Okay, I will show the data sheet of a ferrite.
Okay, that will be easier for me to understand.
Okay.
Okay, we'll look at the question inductor. They have said n equals 10. Air gap they have given, and supplied 100 volt DC across 50 microsecond. Okay, so basically we have to find out something from here. Let us see what we have. We have V equals L di dt. And what data do we have? We have 100 volt equals L, 5 ampere from 0 ampere, so 5 by dt. Dt is, they said, 550 microsecond. Okay, so from here we have to find L. From here we have to find L. So what is L? L is 100 times 50, 10 to the 6
1
by
millihenry.
5. 1 millihenry. Now L, we have n squared times permeance is 1 millihenry. So reluctance we have n squared is 100. Therefore, oh, they have asked for permeance only, so we'll get permeance. Permeance is 110 minus 3 by n squared, which is in 100. What is the unit of permeance? Dimensionally, it should be Henry. Dimensionally, it should be Henry by turns squared, if we can say. Dimensionally same as inductance. So this is the permeance. I think see, the question says that the permeance of the core, okay, but they do not give any data about the cross section area of the core, right? So the permeance that they want to know here is definitely the permeance, overall permeance seen by this winding, not only by the magnetic material. Overall permeance that the winding can see. If they wanted to know the permeance or the reluctance by the core material only, they should have given the area of the core also. Then only we could find out the reluctance of the core, then segregate the two permeances. But that is not given, so this is the net permeance seen by the winding. Understood?
Yes, sir.
Okay. What's the time? 7:30 is enough time. Okay, now some real design problem maybe. An inductor has to be designed for a DC-DC buck converter based on following specs: the input voltage, output voltage, rated load power. Compute the value of inductance in ripple current. Someone asked about, okay, he has left. Anyway, about switching frequency, we could have shown in the problem that switching frequency directly affects the size of inductance. Anyway, so we had this discussion some time back that since the average current in a capacitor is 0 for a buck converter, the average inductor current is the average output current, which in this case is 12 volt, 12 watts, so 1 ampere. Okay, so if this is the inductor current, I have the average of 1 ampere here. Now the actual current is like this, the inductor current is like this. and peak to peak, what is peak to peak is 10%. So delta IL is 0.1 ampere. We have to find out this individual, what have been asked. Compute the value of inductance if ripple current is chosen as 10% rated output current is switching frequency. Okay, so delta IL is 0.1 ampere. Now we have, say, when the switch is turned on, then the inductor voltage is V in minus V out equals L delta IL by DTS. So from here we can find out L V in minus V out DTS by delta IL. V in minus V out is 8. Duty ratio is not given. They have not mentioned CCM also, but we will assume CCM. So duty ratio is 12 by 20, 0.6 times 0.6. TS is 1 by 50 kilohertz times delta I. So this is the inductance that we will need.
So delta I should be 0.1. Huh?
Oh, sorry. So 8 times 0.6 by 50 into 0.1, this much millihenry we will need. Can someone please confirm?
Yeah, sir.
Okay,
Yes, sir.
so this is the inductance value that we will need. Calculate the area product for the inductor discussed uh, in question 6. Okay, so what we have to do is we have to find out the values of inductor current. Values means this I1 the minimum value and this I2 the maximum value. We have to find. What do we have? We have I2 minus I1 is 0.1, that is one equation. We have another equation, we have is I2 plus I1 by 2 average is 1, that is I2 plus I1 is 2. So from this 2 we can find out that I2 is 2.1 by 2.
1.05.
Yes, 1.05 ampere,
0.95.
0.95 ampere. So what we have now, we have something like this, a current which is triangular in nature, whose minimum value is 0.95, maximum value is 1.05 ampere. Now there is one formula, you can derive it also. I am using it directly for now, not very difficult to derive. It is something like, see, if you have, say, if I write it as the minimum current as I1, as I do always, this is I2, then the average current IRMS is square root of, if you already know this, you can confirm once. Okay, I1 cube plus, sorry, not cube, I1 squared plus I2 squared plus I1 I2 by 3. Someone already knows this formula?
No.
Okay, in that case I have to confirm it once. Just a second. Something like this I read some time back. Okay, anyway, till then, can you please find out the value of IRMS and tell me? I2, I1 values we have already found out. Can you please tell me the IRMS value?
That is 1 amps.
Yes, it is correct. Okay, now tell me the value.
Yeah, it is 1 amps. Sir. This current will be 1 amps.
1 amps. This much. Okay. So we have IRMS. Um, our IRMS value is 1 amps. Now, if have they given anything? They have given window factor KW 0.55, maximum flux density BMS 0.25. Okay. Diameter of chosen conductor coil is 0.711. Okay, they have given this diameter of chosen conductor. Unnecessarily, we found out this RMS current. Actually, the rule is that we find out the RMS, then we take some value of J. From there, we find out the dia of the not coil, dia of the conductor. We discussed this last week, but they have given diameter of the chosen conductor of coil is this. Let us find out what J they have taken. Okay. They have taken 1 ampere by 0.711. Oh, this is diameter. Could you please mute yourself? So it is 4 by pi. This is not necessarily, I'm just curious to find out what they have chosen for their design. 0.4 by pi times 0.711 squared. Some 2.5 they have taken ampere per millimeter squared. I think some more could have been taken anyway. So the thing is, it is a area product is area of core times area of window, right? Let us say we are talking about an E core. Okay, so the middle limb what is the area of the middle limb that we need? Now the current is like this, so we have to make sure that at the peak value of the current the maximum flux density is not 0.25 Tesla. Now say if I now write N times I2, equals reluctance how would I know the number of turns? Reluctance. I don't think this question is complete. Any idea?
No idea, sir.
We have to find out the number of turns. How shall I find out the number of turns? Okay, let us take some number of turns n, okay, and see if we can find out the area product I. So, if you have number of turns n, then and then this is bm. Bm we know. Derive the flux. So bm into AC, that will gives the flux. Okay, if I multiply this with n, then this will give me the psi m, which is Li2, right? Out of which we know this, n into AC we don't know. Let us write n into AC. How much is it? L is 1 millihenry. No, sorry, 0.96 millihenry, and I2 is 1.05. So 0.96 millihenry times 1.05 ampere current, that divided by Bm is 0.25, which gives us 4.032 into 10 to the power minus 3. Let us keep it. Let us keep it and see if we can do something here. So number of turns is n we have taken, and they are saying the diameter they have given. So if I put pi d squared by 4, this is the copper area that I need, that divided by window factor 0.55. So window factor kW. So total copper area by window factor, that gives me the area of window, right? So AP times AW, sorry, AP is AW times AC. So AW is n pi d squared by k 4k omega, sorry, kW, times our AC is 4.032 10 to the power minus 3 by n. N gets cancelled. So we have pi, what is d? 0.711. So 0.711 10 to the power minus 3 d squared times 4.032 10 to the power minus 3 whole divided by 4 times kW is 0.55. Let us see if we can get a reasonable value out of it. 0.5 pi times 0.711 times 10 to the power minus 3 squared times 4.032 10 minus 3 by 4 times 0.55. Did I do something opposite somewhere? Do you find any mistake?
Sir,
Oh, wait, I think it is correct. This is coming out as, sorry, see, I put everything in SI. This is meter to the power 4. Generally they give in millimeter to the power 4. Yes, let me see. Yes, they want in millimeter to the power 4. This is meter to the power 4. So we have to multiply it with 10 to the power 12. So that will give you almost 2911. This is an acceptable value. The number of turns get cancelled. That's why. Did you understand the calculation and everything?
Sir, please say it.
Huh?
Sir, please repeat it once. The solution.
Repeat. See, there are two things we have to find out for the area product. One is the AC, area of conductor. Other one is the AW. Sorry, not area of conductor, the area of the core. Other one is AW, the area of the window. Okay. Now, area of core that comes from the maximum flux limit. Okay. So what we have, BM is the maximum flux limit, that times AC is the maximum flux, that times N is the maximum flux linkage, psi M. So maximum flux linkage happens when the current is maximum, so Li2, right? So NBMSC is Li2. So what we got from here, NAC is this, right? We have to find out AC, but number of turns we don't know, so we left it here. And the area, the window area comes from the number of conductors and the thickness of conductor. So number of conductor is n, thickness of conductor is pi d squared by 4, and kW is the window factor that comes due to the gaps between the windings and the area lost due to the former. So that is 0.5, that is given. So that is equal to, so my n pi d squared by 4, that is the total area, copper area that I need, that divided by kW is the total window area that I need, AW, right? So this is the expression for AW here, equation number 4, and this is AC. Now we are finding out AP, which is AW times AC. So AW I put n pi d squared by 4 kW, and AC I put from equation 3, which is 4.032 10 to the minus 3 by n. Now n gets cancelled, so we did not have the value of number of turns, so that is not required, also that gets cancelled, and whatever is left we know the value to all of them, so we could find out of it. And since you see here and here I put everything in millimeter, sorry, everything I put in meter, in SI units, so what we got at the last is meter to the power 4. Now since 1000 millimeter gives you 1 meter, so it's 10 cube times 4, so 10 to the power 12, if you multiply you get the same thing in millimeter to the power 4 units. So this is what you have to find. The data sheet they give this value, that's why I was initially confused why it is so small, but then I realized that we did everything in SI, so it is correct. Is it clear?
Yes. Yes.
Yes, sir.
Yeah. It's already 8 p.m. Okay, we will complete this question. Last question. Okay, last two questions. I think this will be solved tomorrow. Maybe we will
Yeah.
see how much we can do. A city has one primary turn and 100 secondary turn. City's current transformer. Okay? So N1 is 1, N2 is 100. It has a core cross section of 25 millimeters squared. This city is connected as PT in the forward converter configuration with 1 turn in the primary, 100 turn in the secondary, allowing flux density to swing up to 0.2 Tesla. Core demagnetizing is achieved using a Schottky diode and resistor configuration connected across the primary. If the forward converter is switched at this frequency, this duty cycle, what is the output voltage of the forward converter? Okay, so basically this question is simply that you have been asked to find out the output voltage of a converter while the inductance value is indirectly given, or something is indirectly given. We'll find out what is indirectly given. So what do we have? We have V output is V input times N2 by N1 times duty ratio. We have been asked to find out V output while just a minute. 50% duty ratio is given. Okay, so N2 by N1 is 100 times half, so 50 V in, right? So we know that V output is 50 V in, so we have to find out the input voltage. So how to find out the input voltage? Input voltage they have indirectly told by giving this statement, allowing the flux density to swing up to 0.2 Tesla. And 100 second, okay, 25 millimeters squared. Let us see what we can find out. So V in equals V in is d psi dt. We can say delta psi dts. Delta psi is n delta phi dts. This is primary side. Primary side n is 1, so delta phi dTs, phi is b dot ds, b dot area, so area of core times delta b dTs. Now you see they have said that the winding is being reset by a Schottky diode and a resistor. In other words, the winding is being reset very fast. Schottky diodes are very fast. Okay, that means we can assume that at the beginning of every switching cycle, the flux is starting from zero only. It is reduced to zero because the demagnetizing is very fast because of the Schottky diode, and the flux is starting from zero only. So whatever the delta B, that starts from 0 to this much, so 0.2 Tesla. So what is required? I think we know everything. So area of area of core 25 millimeters squared, this time 10 to the power minus 6 meters squared times, please give me a moment, just a second. অর্ক আমার 5 মিনিটের মধ্যে হয়ে যাবে। হুম 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 ঠিক আছে ঠিক আছে। So this times delta B is 0.2, duty ratio is 0.5, and TS is frequency 100 kilo. So what do we have? 25 10 minus 6 times 0.2 times 10010 cube by 0.5. 1 volt is coming. So V in is coming out to be 1 volt. And V out is then 50 volt. Is it clear? Easy question. Only thing what they have done is they have given some information about the magnetic circuit, and they have said that in this much time this much is the increment in flux, so from there we can find out the input voltage. Rest is just the equation of forward converter, from where you can find the output voltage.
Sir, here we have used only PT, right?
What?
Sir, here we have used only, we have taken N to be 1 because we are using PT.
They have mentioned it here with 1 turn primary and 100 turn secondary.
The CT, what may be the reason, sir, behind it? The CT
Just
information they have given.
forget that those are only to confuse the students. Be it CT PT, simply take it as a transformer which has N1 is to N2 as 1 is to 100, just like that. CT PT you forget. This is clear, no, this solution?
Yes, sir.
Okay, 2 more questions are remaining. I think we are already beyond time today. This will be covered tomorrow. There is another session at 6 p.m. It will be covered there. Okay. This is an easy question. Inductors shown. Last question you already know. For DC buck-on application size of what is the possible option to reduce size of core from the given options, whatever, without compromising on ripple current and rated load current? So they are saying that you cannot change the ripple current. So we have, V in equals L delta I by dTs. So L is V in times D by frequency times delta I. So I cannot, they're saying I cannot touch this, I cannot touch this. No, they did not say that. I cannot touch output voltage, so this. So the only way to reduce the inductor size is to increase the frequency. If I increase frequency, L will reduce. This question will give you a hint and then go. Shown figure below, mean length of ferrite core is this and length of air gap is this. Relative permeability of ferrite core is this. Calculate the number of turns required for. This is easy. This is just that discussion that we had just some time back. We have reluctance of the gap and reluctance of the core. Reluctance of the core is given by L by mu naught mu r times area, which is 50 millimeter. Okay, whatever value you can put. This is reluctance of the core, and reluctance C and reluctance of the gap is Lg mu naught Ag. So reluctance, if you find out, then the net permeance is 1 by Rc plus Rg. Calculate number of turns required for inductance of 5 million. So N squared permeance is L. So N is square root of L by P. Doable, no? You can understand the steps?
Yes, sir.
Okay, we'll stop the meeting then for today. Next week we will meet with, I think, another lecture of isolated DC-DC converters.